Welcome friends and welcome to my series of video lectures on design of RCC structures. This is the first lecture in chapter 5, Shear Design of Beams. The title of this lecture is Behavior of Beams in Shear. For best video quality, watch the lecture on laptop or desktop with resolution set to 1080p, that is HD. The expected learning outcomes from this video lecture are 1. To explain behavior of beam in shear. 2. To draw pattern of shear crack propagation. The contents of this video lecture are 1. Shearing action in beams. 2. Shear crack development in beams. We are going to use some key terms in the lecture. Design criteria. Pure shear, shear design, diagonal tension, diagonal compression, shear cracks. Now, here is our best friend Smarty with some smart tips. Write down your own notes while watching the video. Pause or rewind the video whenever required. Do solve the formative and summative assessment quizzes provided at the end of the video. Friends, in this part of this video, we are going to study shearing action in beams. Here is a very familiar picture. This is a construction site of a building going on. So we have got these horizontal members as beams and the vertical members of columns, and this is a typical beam column system. Now technically we define the beams as horizontal structural components supported on columns to support loads of slabs and walls. So that is the definition of beams. Now when we want to design the beams, we have to design the beams but to follow or to satisfy the 5 design criteria for beams. So beams are critical for the following 5 design criteria. These design criteria are classified in 2 limit states. In limit state of collapse, we have got flexure, that is bending, shear and bond as the 3 design criteria. Whereas in limit state of serviceability, we have got 2 design criteria, cracking and deflection. So in all, we have got 5 design criteria for the design of a beam. Now, here we see the mathematical conditions the beam should satisfy in order to satisfy these design criteria. So for flexure, as we have already studied in the earlier videos, the beam has to satisfy MUR, that is moment of resistance, should be greater than maximum bending moment. That is the basic equation we have to satisfy. By satisfying this equation, we get the values of B, D, AST and ASC. That means the size of the beam, the cross-sectional size as well as the amount of bottom steel or top steel is defined by the design for flexure by satisfying this condition. Next is shear. For design of shear, we have to satisfy the condition VUR, that is the resistance in shear. VUR is shear resistance of beam should be greater than VUD, which is the maximum shears developed in the beam due to loads. Now, this shear design will give us the output of the spacing of stirrups and the provision of bent up bars. So that is the outcome of shear design of beam. Now the third criteria, design criteria, is bond. For bond, we have to check that the development length LD actual is greater than development length required. This gives us the design output as anchorage length whenever required. So these are the mathematical equations that give us the design outputs according to the design criteria. Now for serviceability, we have got 2 design criteria, cracking and deflection. We have to follow the code provisions for rebar areas, covers and spacings. So whatever reinforcement we are going to provide from the design, or that IS code has given some specifications about the area, cross-sectional area, the distance is called covers as well as spacings. So if we follow these provisions from the IS code, then we can say that the cracking is properly taken care of. Then the deflection is also taken care of when we follow the code provisions in terms of L by D ratios. The cracking and deflection and bond will be covered in subsequent chapters of the design. So in conclusion, we can say that whenever we look at a beam, we have to bring into our mind these 5 words and these 5 concepts: flexion, shear, bond, cracking and deflection as the design criteria for a beam. Now in this lecture we are going to study the shearing in beams, the design criteria which we are calling it shearing. Okay, so let us understand the structural action of shearing in case of RCC beams with a greater detail. First point, why shearing occurs in beams? We know that a beam is primarily a flexural member, that is, it responds to the load by bending. But in beams, we find that the shear forces arise due to variation in bending moment along the span. That means we find that the bending moment is not constant along the span, and that variation in bending moment gives rise to shearing forces in the beam. Let us have a sample example. Look at this beam loaded with UDL and a point load, a simply supported beam. We are very much conversant with this SFD and BMD. In structural mechanics, we have drawn these SFDs and BMDs for very complex beams also. Now, if we just look at the bending moment diagram, we find that the bending moment is changing from one point to the other throughout the beam. Nowhere we find a constant part in the bending moment. So the bending moment is constantly changing. It may be increasing or decreasing, whatever, maybe positive or negative. It is constantly changing. So due to this change in bending moment, at every change in bending moment, that means at every point we get some shear force. So the direct relation, as you know mathematically, the relation between bending moment and shear force is that shear force is the rate of change of bending moment. Numerically we can say that, and that is why we can say that variation in bending moment is the cause of existence of shear force in beams. Now let us see another example. This is also a beam. This beam is a simply supported beam carrying these 2 point loads P and P, which are symmetric at a distance A from both the supports. Now if you draw the shear force and bending moment diagram of this beam, you will find that the shear force diagram will be having one rectangle here and another rectangle here, and this line will be zero shear line. The shear force along this line will be 0. So right now we said that the shear forces arise due to variation in bending moment. Since the shear force is 0, it means that during this portion or between these 2 points, the bending moment variation will not be there. So if you look at this bending moment diagram, you can confirm this fact that the bending moment is increasing from 0 to PA, value PA. Thereafter it is constant. Horizontal straight line indicates that bending moment is, so it is constant bending moment, then again decreasing bending moment. So whenever there is a change in bending moment, we are getting a shear force diagram. But whenever the bending moment is constant, we are not getting any shear force diagram, zero shear. So this bending moment diagram clearly illustrates the example of variation of bending moment and its relation with the shear force. Now we can say that when we are talking about any cross sections between these 2 loads where the shear force is 0, we can say that this in this portion of the beam is undergoing what we call as pure tension. I mean pure flexion or pure bending. So it is subjected to pure bending, and otherwise this is not pure bending. This is bending mixed with shear. So every time most of the times you will find that in beams we get some shear force as well as some bending moment at every cross section. That is why in beams we get bending mixed with shear, and that is why it is important to study the shearing action in beams along with the bending action. Now let us go one step ahead of this. Bending causes normal stresses sigma x in longitudinal layers, and shearing causes tangential shear stresses tau xy in the beams. So this second statement tells us one more step or one more part about the action of shearing in the beams. So we have right now seen that in the beams we can get a combination. We get a combination of shearing and bending in general. So bending stresses, they cause normal stresses sigma x in longitudinal layers of the beam. So if you look at the element in the beam, you can take these squares, as you are aware, they are the elements of the beam. So they are enlarged points of the beam. We call them as elements, infinitesimal elements. You might recollect the topic of principal stresses and strains, which we might have studied in structural mechanics or theory of structures. So this takes a back reference of that chapter. So here you can see that it's sigma x. In every element you find sigma x and sigma x. The sigma x stresses, these are normal stresses, and they are caused due to bending. So if you look at this element, normal stresses due to bending plus shear stresses due to shearing. You can see these tangential shear stresses also. Tau xy represents shear stress. You know that shearing stresses are shown in 4 arrows, in the form of 4 arrows, because they are complementary to each other and complementary shear. So shear stresses will always exist in 4 arrows, whereas normal stresses can exist in 2 arrows or 4 arrows. So this is sigma x and these are. So this is an element having normal stresses plus shear stresses. Now this is another example, second example, in which you can find only normal stresses. Only normal stresses. The normal stresses are caused due to bending. So this means that this element is subjected to only bending, pure bending, and no shear stresses. Right? So this is the second case. The third case is there are no normal stresses. You can see the sigma x stresses are absent and you find only shear stresses here. So this is where you get pure shear. Just as this was pure bending, this is pure shear. You can see pure shear. This is pure bending. So pure shear means no mixing or no mixture of bending with shear. So this is the element in pure shear. The element in pure shear is most critical as far as the shear design of the beam is concerned. So otherwise, here you will get a combination of the two. Here you will get only normal stresses and here you will get only shear stresses. Now we will analyze this pure shear element a little bit more. Okay. Now if you just look at this element, if this is subjected to only shearing stresses, due to the action of the shear stresses in the direction of the arrow tips, you will find that this diagonal of the element will get elongated or stretched, whereas the other diagonal will get contracted. So we will say that along this diagonal there will be tension developed, and along this diagonal there will be compression developed. So we will say that when an element is in pure shear, we get diagonal tensile stresses and diagonal compressive stresses perpendicular to each other in the element. So this element gives us the idea that even though the element is subjected to pure shear, finally it results in diagonal tension and diagonal compression. So the pure shear action or shearing action finally eventually leads us to diagonal tensile stresses and diagonal compressive stresses. So this is how we can say that when principal tensile stress exceeds tensile strength of concrete. Now let us go one step ahead. Here we find that due to shearing stresses, we get the diagonal tension and diagonal compression. Here we are considering the element which is in pure shear, that means their bending moment is not acting, right? So bending moment is zero and you are getting only pure shear. So in that case, if concrete is sufficient, okay, its concrete is sufficient enough to resist the stresses, then you can say that the beam is safe. But we know that concrete is weak in tension. So concrete is not able to resist this diagonal tension arising due to shear. And that is why we have to provide shearing reinforcement. We have to take help of steel to resist this diagonal tension in the shear design. Now there is diagonal compression also. Concrete will be usually sufficient to resist the diagonal compression, but concrete will not be able to resist diagonal tension, and that is why we have to provide shear reinforcement in the form of stirrups or bent up bars and so on, that we will see later on. But this diagram tells us why it is needed that we provide the shearing reinforcement. What is the need of shearing reinforcement? The need of shearing reinforcement is that we get diagonal tension developed due to pure shear. Why shear is developed? Because there is a variation in bending moment, and that is why this is the critical situation. In the beam, you will get at various points, you will get this situation or this situation or this situation. So this slide has described that how the shearing action in beams takes place. Friends, after having discussed the details of shearing action, we will now consider a example of a simply supported beam, and we will try to understand how the beam fails in shear. What sort of cracking pattern we get when a beam fails in shear. For that, let us consider this simple example of a simply supported beam. This is a simply supported beam carrying uniformly distributed load W over its entire span. Now, we are all conversant with the shear force diagram of this beam and bending moment diagram. We know that for this beam, the shear force diagram is in the form of two identical triangles, and the maximum value of shear force is at the support, which is WL by 2 at both the supports. This is positive shear, this is negative shear, and the shear force value is 0 at the center of the beam. Now there is a reverse situation in case of bending moment diagram. This bending moment diagram is a parabolic curve, a sagging or positive bending moment diagram. It is having maximum value of bending moment M max as WL square by 8 at the center, and the values of bending moment are 0 at the two supports. So if we compare the two diagrams, SFD or stator shear force diagram and bending moment diagram, we will find a reverse situation that the beam is, when it is critical for bending at the center, it is critical in shear at the supports. So the sections which are critical for bending moment, they are not critical for shear, whereas the sections which are not critical for bending, where their bending moment is 0, whereas here the shear force is maximum. So we have, while designing, we have to be very careful about which section of the beam we should address for the design calculations. For bending, we have to use the mid-span section, the middle section, because from the bending moment diagram it is clear that we are having bending moment maximum at the center. Whereas when we are designing the beam for shear, we don't have to concentrate on the central portion here, but we have to concentrate on the support sections. which are showing maximum values of shear force. Now we will proceed further to understand how the failure of the beam of this beam will occur due to shear. So we will take help of this diagram. If we look at this diagram, this beam has been shown enlarged. Here are the two columns. We see that these lines, they appear to be zigzag or random, but they are very carefully drawn. They indicate the cracks. So when the beam will be overloaded and when the beam will be on the verge of collapse due to shear, then what will happen to the beam? That we have to see. Before that, in the earlier slide we have seen some elements, infinitesimal elements showing normal stresses or shearing stresses or whatever. So here we will see the example of that. Here you see this element, right? This element is having central element, okay? This is at the center of the beam and it is at the bottom of the beam, right? So you know that this is sagging bending. Due to sagging bending, you get tension at the bottom and you don't get any shear forces. The shear force is zero. So you see in this element, if you look at this element, this square element, you find sigma x only normal stresses. There are no shear stresses shown because the shear force is zero according to shear force diagram at this particular section. So at this particular section, the situation is that the beam is subjected to only tensile stresses, and these tensile stresses are the flexural or normal tensile stresses. So due to that you find this crack, this particular crack which has started as vertical crack. So this vertical crack indicates that it is a flexural crack or a crack due to bending. Now look at the element shear. This element is near the support. You can say it is close to the support. So closer to the support you find that the bending moment is getting reduced and you can say that the bending moment is zero here. So you look at this element now. Here you don't see any sigma x. The sigma x is not there, which means that the bending stresses are not there and the element is considered at the center, that is at the center of the beam. You may say this is the neutral layer. At the neutral layer and at the support, we find that the element is in pure shear. Why it is pure shear? Because only shearing stresses are acting. No bending stresses are acting. No normal stresses are acting. So this is an element in pure shear. So here I think you can understand the application of the earlier slide that we saw three types of elements. The one of them is seen here and the other is seen here. Here it is pure shear, here it is pure bending. In between, at any point you can show this element and you can get the idea that in between you will get both normal stresses tau x, I mean sigma x, as well as the shearing stresses tau xy. So these are two extreme cases. This is the extreme case for bending. We are not right now concerned with bending. This is the extreme case for shear. At the support you are getting an element in pure shear. Tau stands for shear stress. So tau xy is the highest value of shear stress developed at this section. Now we have also seen in the earlier slide that due to this pure shear, this red dashed line you can see, this line indicates diagonal tension. Diagonal tension will be developed and concrete is weak in tension and that is why it will fail and you will get this crack. This crack is perpendicular to this diagonal tension line. Obviously, this crack is because this diagonal tension line, diagonal tensile stresses could not be resisted. That is why the concrete has undergone this cracking. So this is a 45 degrees inclined crack due to diagonal tension. This is the typical first crack you will see in the beam when it will start its collapse due to overloading due to shear. Now we can see here that similarly the cracks and their directions are shown here, and accordingly we can say that the shear cracking regions are formed in the beam. You can see that there are regions. This is 1 up to this point to this point, region 1, region 2 and region 3. Similarly, region 1 here, region 2 here and region 3 here. Out of the 3 regions, region 3 here and here, region 3 is close to the supports, and that is where shearing action is prominent, whereas region 1 is at the central part of the beam where the shearing action is weak. Shear is not much, but bending action is prominent, right? So the cracks will also be according to the action. Let us just understand region 1. Look at region 1. Just read the words. Middle region. Region 1 is the middle region. Vertical bottom cracks. These are vertical. Okay. These are not inclined like this, 45 degrees or anything. These are vertical, and at the bottom they are vertical, right? They are vertical bottom cracks where bending moment is large and shear force is very small. Theoretically, at this point shear force is 0, but in the region, if you say, the shear force will be slightly, it will be gained slightly, right? So there will be a slight increase in shear force from 0 as we go from here or there. So this is the description of region 1, that the bottom and vertical cracks are here. Now the other region is region 3, which is the other extreme. So we will consider region 2 later on. The region 3 is shear prominent region. Shear, the region 1 was bending prominent region. This is, so what is the description about region 3? Region 3 is region near supports. Shear cracks due to tension are formed. So shear cracks due to tension means, here the tension means diagonal tension. Diagonal tension due to shear. Okay. Here in this case, this sigma x was also tension. It was not diagonal tension. It was normal stress tension, and it was a flexural tension. So at the same time you get flexural or bending tension in the middle region, whereas the diagonal tension in the support region. That is what we have to understand. And accordingly, the direction of cracks are also different. Due to bending tension, you get vertical crack, whereas due to diagonal tension, you get a crack perpendicular, 45 degrees, inclined at 45 degrees with the horizontal. So regions near support, shear cracks due to diagonal tension are formed along the diameter, called as web shear or diagonal tension, where shear force is maximum. So shear force is maximum here, so you get these diagonal cracks, diagonal tension cracks. The diagonal compression is also acting there, but it will be taken care of by the concrete itself, so we don't have to be afraid of those cracks. Now the middle region, this intermediate region, region 2, which is between 1 and 3, this region is having combination of bending as well as shear. So here that third element comes. So we will see both shear force and bending moments are present. Look at the region 2. This is the region 2. If you look this region 2 diagram, you can see that there is some shear force, there is some bending moment. None of them is maximum or minimum. Both of them are having some value. They are not maximum values or minimum values, some intermediate values. So we will say that the element somewhere here will be having both the types of stresses, shearing stresses as well as normal stresses. So here both shear force and bending moment are present. So crack is initially vertical at bottom. Just understand this. Crack is initially vertical at bottom, but gradually tends to bend in diagonal direction towards the neutral layer due to increasing shear. So slightly it goes on, initially it is vertical, it was vertical in the bottom, but now it has become inclined. As you go towards the support, as the shear force becomes prominent, and the bending moment becomes less prominent. You will see that the direction of the crack is also. So from vertical to 45 degrees inclination, that is how the crack inclination changes from the center point to the supports. So that is the message. And also the at this support again you get 45 degrees inclined cracks, just similar to this. So this is how we see the propagation of cracks, and these support cracks, these are the shear cracks, and to resist these shear cracks we have to design the shear reinforcement, which is going to be the topic for the next chapter. Now we will see a practical example. You can see this particular beam and you can clearly see a 45 degrees crack developed, and you can see some reinforcement bars also getting exposed. The collapse has already taken place and you can see this 45 degrees crack in real situation beam. So when there is a shear failure, it starts at the supports and it is having 45 degrees inclined cracks due to diagonal tension. Now this situation, these cracks, this crack pattern, everything was in this case for a simply supported beam subjected to UDL. This was just to make us aware of how the shearing action takes place and how the cracks are developed. With this understanding, with the insight of this example, we can apply the same concept to any type of beam. For example, a cantilever beam or an overhanging beam. Also in case of even a simply supported beam with different loads other than the UDL, we can apply the condition. Just compare the shear force diagram and bending moment diagram, and accordingly you should be able to draw the diagram showing the propagation of cracks. So this was the part of the lecture in which we studied the shear crack development in beams with the example of a simply supported beam carrying uniformly distributed load. Now friends, before we come to the conclusion of this lecture, we will have a formative evaluation test, self-test. So pause the video and write on a paper the answers of the following questions. In this lecture we have studied behavior of beams in shear. So answer these two questions based on that. 1. Describe behavior of beam in shear. This is an understanding level question. It's a descriptive question. So second question is draw a diagram showing shear crack propagation in a beam. So this is also an understanding level question. If you have given enough time for these questions, you just proceed for the video. So finally, let us sum up. This was lecture 5.1 in which we studied behavior of beams in shear. The expected learning outcomes from this video lecture were: 1. To explain behavior of beam in shear. 2. To draw pattern of shear crack propagation. We studied the contents: 1. Shearing action beams, and 2. Shear crack development in beams. We used some key terms: design criteria, pure shear, shear design, diagonal tension, diagonal compression, shear cracks. Friends, with the help of these keywords, try to recollect the contents that you have listened or studied in this video. Try to find out whether you have really attained these learning outcomes. Are you able to confidently explain the behavior of beam in shear or draw the pattern of shear crack propagation? And accordingly, if required, you can take help of the teacher. Contact your teacher for any doubts or queries. You can rewind the lecture and pause it and frequently watch the video again. Summative assessment quiz in the form of Google quiz is provided for this video lecture also, as usual. In the description part of the YouTube video, you will find the link for the Google quiz. So attempt the online summative assessment quiz provided by the teacher, because the test is the best judge for you whether you have really understood the things or not. Now, the next video lecture RCC 5.2 is going to be our IS specifications for shear design of beams. So with this, I think here Smarty is back with us to say us thanks. So thanks for watching this video and goodbye till we meet next for the next video.